Hey guys, my name is Parth and we'll be going through lab number 2 of INCS 745. So basically this lab is all about different TCP IP attacks. And in the first task, we'll be performing a DOS attack called SYN flood attack. This attack will just blast off the server with all the SYN requests. And the next one is a reset attack. For in this attack, there'll be two parties communicating with one another, and we will pick one of them out of the communication. The third one we will do, as the name says, we'll do system hijack. We will try to get it between the communication that was going on between two machines, and we'll get in between them, and we'll send requests on behalf of one of the target. Then the last one is basically a better version of the previous task. So we'll get in between the communication and we'll implement a reverse shell on the victim to get the persistent access to their machine. Okay, so that was all for the basic tools. Before jumping straight into all the tasks, I have to give some brief explanation on how this lab's going to work. So this lab will be using only Docker containers. You don't have to turn on our server virtual machine or the second virtual machine. It's the student one or attacker one will be just fine, but it will take up a lot of memory. These tasks of these labs are going to consume plenty of memory. So yeah, it will slow things down quite a lot. So let me show you how things actually going to work here. So, as I've said, we'll be using Docker containers. There will be a total of 4 containers. One of them will be attacker, one of them will be victim, and there will be two users, regular users. Although user number two, we are not going to deal too much with user number two. User number one is going to be really point of interest for us. And unlike the previous lab, we are not going to have not every single person is going to have different IPs. We are just going to run this in student virtual machine as a Docker containers. So the IP will be same for you guys as well. So the attacker's IP will be ending with 1 and the victim's IP will be ending with 5. User one's IP will be ending with 6 and this 2 will be 7. But yeah, that was all for the basic thing. Now I'll give you some brief explanation on what kind of task we are going to perform. We have discussed the name of the task. Now we'll give you some brief introduction on how it actually works. So in Sinflood attack, this is how we actually things go. So the attacker sends a scene request. Attacker sends a scene packet saying hi. And victim will be responding with syntax. Hi, would you like to connect? And as a result, attacker will be just ignoring the syntax packet of victim. So the victim will be still waiting for acknowledgement packet from the attacker, and victim will keep this thing is called half open connection. Yeah, write down. It's called half open connection. So the victim will be keeping track of all these half open connections. So this half open connection would get stored over here in the memory. I will describe that as well. So this half open connection gets stored over there. So, like this, attacker will keep on blasting the victim off with this SYN request, and victim will respond back with SYNAC. This thing will keep on growing, and victim will keep on waiting for the ACK request from the attacker. But the attacker is not sending any ACK request, ACK packets at all. So victim will keep all of these half open connections in memory, and eventually will run out of memory like that. So let me show you how this memory thing actually works here. So it's like there's a thing called max in backlog. It's a buffer it's a thing like buffer here. So in this backlog, every single machine has a limitation of backlog. like regular memory, you have 2 gigs, 4 gigs. In the backlog, there's a limitation like 80 connections, 90 connections, etc., etc. So it's a buffer-like thing in memory. So in this buffer, first couple of spots are reserved for established connections. It's like the backlog keeps track of established connection in memory. So when the connection is established, it gets stored into the reserved spots. And when they want to reuse the connection, they can use it from there. But the rest of these half-open connections are stored here. So victim will keep on storing this half-open connection until the buffer is filled up. So once the buffer is filled up, there won't be any half-open connections in the memory. And eventually, if let's just say user one wants to connect with the victim, the user one won't be able to connect because there is no space left to store the connection for user number one because all the real spots are already there and the rest of the spots are filled up with half-open connections. So there is no way the regular or I mean user number one will be able to connect with the victim. So it's just simply like buffer overflow, but in slightly different way. So everything will get filled up, and eventually the victim will start dropping all the upcoming packets that will be coming. So that was for the backlog thing, but there are plenty of other countermeasures that we will describe once we go through it. So the next one is, as I said, it's a really RST attack. We will kick one of the parties out of the communication. So let's see how it goes. So first of all, in this attack, we will try to simulate an environment where user one is has established a connection with the victim on telnet port 23. However, here the attacker will check the network traffic, how things going on in the network, and attacker will try to predict what will be the next packet of user one, what kind of packet the user one will be sending to victim next. And once everything is figured out, the user one will attacker will try to figure out what should be the source IP, what should be the destination IP, and all that. So once everything is figured out, attacker would send an RST request. RST basically is like a short form of reset. So attacker it's just like type of request like SYN-ACK and SYN-ACK and all this. And there is also called RST. So attacker will send an RST request, which is basically used to terminate the communication. So attacker will send RST request to victim, and the victim will be. So this RST request will be kind of spoof. Attacker will pretend as a victim, not victim, as a user one. So the attacker would send the request to victim, and victim will be like, this request came from user number one. I got it. So I will close the connection with user number one. So that's how you will just picking user number one out of the communication. That's the only thing you're going to perform in task number two. So number three is session hijacking. Just like the name says, we are going to hijack this session of user number one here. So it will follow the same initial procedure of checking the network traffic and predicting what will be the next packet from the user number one. However, here we are not going to send a reset packet, we are going to send an acknowledgement packet. So the acknowledgement packet would require a bit more information, like acknowledgement packet would require sequence number as well as the acknowledgement number. All that will figure that thing as well. So once everything is done, the attacker will also try to attach a malicious payload with the packet. So once it's done, attacker will send it to the victim. Attacker will send it to the victim, and victim will think that this comes from a reliable source, that is our user number one. So victim will think, okay, this is safe. Let's just do it. So our malicious payload will get triggered and will eventually the payload is created in such a way that the output should be sent back to the attacker, not the victim. So we'll see that as well. And number four is basically a better version. of task number 3. It's a reverse shell. We will be swapping the reverse shell to the victim's machine and get more persistent access to the machine. So like the previous one, we'll just sending out one malicious command and everything will be done. Here we'll be dropping the backdoor or reverse shell or whatever you can call it. And it's the same thing, but we are going to use a different payload. So that was all for the basically what we are going to do in this lab. So now let's just go one by one. So it's the same thing that we'll be using for double containers and all that. Also, make sure that you don't follow 2.1 from this manual because we have done all of this in our lab prerequisites. So follow the lab prerequisites instead of this one because there will be a slight difference between the command like instead of PC down there will be instead of where is this yeah instead of doc PS we'll be running DCPS and instead of doc SH we'll be running DCSH. So it's like shorter, not the longer one like doc SH and all that. So let's just go through the basic lab setup once more so that you guys don't face any problems while performing this lab. So first of all, first goal is to make sure that the local containers are up and running. So we'll go to desktop, TCP attacks. There's a folder here. Yeah, there's a folder for TCP attack. So we'll go to the same folder in terminal, TCP attacks, and we will run this command, PC up. So this command will turn all the containers in one go. Once it's done, we'll create a new tab. We'll create a couple of new tabs. All right, so now the tabs are created. We will make sure that everything is running. Okay, so now we will try to do get the Docker ID of all the containers. We got the name over here, but now we need ID as well. So for that, there is a command called DCPS. So over here, it's called docps, but we will be running just DCPS. So make sure to run DCPS. Because if you run docps, it will just say command not found. So we'll just run TCPS and it will give us all the IDs as well as name. So this is the name of the container. This is going to be the ID. We just have to look for the IDs and yeah, let's just do this. Okay. So in this tab, I'll be going into the shell of attacker double container. So there's a command dcsh. So over here it's docsh, but we'll be just doing dcsh. So dcsh plus will be running. So let's say I want to get into shell of attacker container, seed attacker. So we'll just write down first two digits of this ID. So dcsh 26. So for 26, it will be attacker container. Now we are into attacker's container, and as I've said, the attacker's containers IP of that attacker's container ending with a 1. This will be 10.9.0.1. So I will just do config to confirm that ID is ending with 1, IP address is ending with 1, and here's the ID, it's ending with 1. So we have confirmed that now we are into the attacker machine. So we'll do the same to connect with the other machines as well. So the next one is victim. So for victim it's 76 here. So we'll do DCSH 76. And we'll do the same with user 1. So user 1 is 01. We'll go with 01 then. DCSH 01. So now everything is done. We're not going to touch number 4 at all because for now there is no use. You can use third one as in any of the tasks. Yeah, for now, in the demonstration, I'm not going to use fourth one. Okay, so now we are into all the containers. Number 6 is for the attacker, number 76 is for victim, and number 01 is for user number 1. Okay, so everything is done, and we'll do a couple of things. Okay, so now we'll go to lab menu task number one by one. Okay, so as I said, here the user number one will be connecting with the victim. So, and also we are going to use telnet here. Let me just go a bit up here. Yeah, here as you can see, we are going to connect. User one will be connecting with the victim on telnet port 23. So that's like we are simulating a real world scenario of one user connecting with the server. So here the let me confirm one thing that user one is 01. Okay. So user one is using telnet to connect with the victim's IP is with 5 and on port number 23. So now we are connected and it's asking for login details. Login details is already given in lab menu. You can see here they already created account called seed and the password is reverse of seed. It's called this. So we'll put the login name seed and the password is seed. So now we are into the now we are connected with the victim and yeah, we are in now. Okay, so now we have established the connection here. We'll get out of the connection now. So that was just for the demonstration that this is how you can connect with the victim in this lab. Okay, so now we are going to do SIM flooding attack. So before I discussed this earlier that this is just regular TCP handshake seen again the attacker now client has sent back an acknowledgement request and the prevents it is completed. But in this case, we'll be sending a send request. We'll be sending plenty of send requests. The server will be responding with SYNAC, and the response attacker won't be sending any ACK requests. Although here there will be a bit of change because we'll be using a random IP as well. So yeah. So but the server here is going to wait for all the acknowledgement requests. So we'll be waiting and keeping all the half-open connections in memory. Eventually, the memory gets filled up and will start dropping off all the next incoming packets. And this is the concept of backlog that I was talking about. There is a memory for like thing that stores up to 128 connections. In 128, there will be around 70 to 80 for half open, and the rest will be for already established ones. So we can run this same command in, let's say, victim container to see what's the backlog size for the victim. So if we will run that dot IPv4 dot TCP underscore max sin, let's see, well, let's net dot IP4 TCP. Oh, it's not MX. Yeah. So we got here backlog is 512. So the interesting thing over here is if the backlog is higher, then there is a good chance that our attack will fail. Because it's just like memory. The lower the memory, it's easier, lower the buffer size, easier to exploit them. The higher the buffer size, there's a, in sort you can say the server has a good capacity to store all the half-open connections. So let's just say if the backlog size is around 60, so the server will be just storing up 60 connections and then start dropping the rest. If the size is 512, then the server will be storing up to 512 connections and then it will start dropping. So the lower the size, the better the chance our DDoS attack to success will be. So that's how backlog works. We can check it as well if you do net stat, yes, in the key. So right now there are only few connections, but once we'll start doing our DDoS attack, then all the random requests will be dropping over here. So then the rest of the requests will be shown up in this thing. All right. So that's all about that. And also, as I said, there are plenty of different countermeasures for this thing. The DDoS attack is really common and easy to perform, so there are plenty of different countermeasures, and one of them is called sin cookie. So sin cookie is an interesting one here. So sin cookie is like, as I said, the whole thing gets stored in memory. So sin cookie, if the sin cookie is enabled, it won't store anything in memory unless the connection is established. So it will make our attack completely useless. Even if we just blast the server off with SYN requests, the server will be still up and running because it's not even in the memory. That was all for the SYN cookie. Another countermeasure will be here. Yeah, and it also says how you can turn on SYN cookie or how you can turn it off. And I think in task number 2, you are also going to perform the DDoS attack while the SYN cookie is on, and you'll be explaining what's the case here. Okay, so now we'll go to task 1.1 and it's called launching the attack using Python. We'll be running this. You're given the Python script over here. You just have to copy this whole script and paste it in your terminal. That I've already done it, but still I'll show you guys. So we'll go to volumes. Make sure to paste your script in this volumes folder like RVS, I guess. Not RVS, not this one. Let me check where this script is. Oh, never mind, I'll just do it now. So we'll just copy this full script and create a new report, py. We'll just paste the script over here. Oops. Okay. So in this script, there are a couple of things like the stars in random places. So instead of stars, we will be putting our own information that will be relevant to this lab. So for example, we are going to do a DDoS attack here. So the destination of this whole thing will be the destination IP of our target, which is going to be victim. So instead of the stars, you'll be putting your victim's IP. I'm not going to write down the IP. Never mind, I'll just do it anyways. Oops. So let's just say my IP is so so let's just say if my IP is going to be 10.0.0.5 because it's a victim's IP, so that will be the destination IP, and let's just say the port number is now 23. So we will just do here 23, and the flag here is going to be S because it's a SYN request. Also make sure that this thing is correct. So the flag is set to S because it's going to be a SYN request. And in the while loop, we'll be doing some interesting things here. The while loop, first of all, is going to run an infinite loop. Let me just put this one. Oops, not this. Okay. So in the while loop, there are a couple of things going on here. It says packet.ipsrc equal to this thing. So this one would randomize all the source IP. This one would randomize source port, and this one would randomize sequence number. So to make the attack even a bit more stealthy, so that all the requests will be coming from different IP, different ports, eventually make confusing the firewall, whatever the defense mechanism is. So we'll just run the Python project. For this one, we'll go to this tab. If we go to volumes folder, we can see our created Python script in here. So previously, I showed you guys that, let's just do it again. So it will tell it same dot or dot. 5 and 23. So we'll try to connect with the victim right now, and it's successful. We can connect it with the victim. Now we will be running the script, Python script, details.hide. Also, to make things easier, I will the Wireshark as well. And one thing you guys have to keep in mind here is that, unlike the previous lab where we have selected this network interface, ENPOS3, because it was between two different virtual machines, here we are going to use the this one that's starting with BR, because it's kind of like a virtualized Docker interface thing. So here we are going to use this one instead and to start fetching packets. So we'll be running the script, and yeah, you can see here it's now blasting the server off with the different request. You see? So let's just say it's randomize IP and also randomize ports. And eventually, if you try to connect with if the user one tries to connect with this thing, it will be a bit slower. So it will keep on trying. So the reason why it's happening is backlog size. So backlog size is now 5 and 2. If you reduce the backlog size to even smaller, let's just close this thing out. So if you reduce the backlog size to, let's just say 128, let's just put it to 80. Now the backlog size is 80, and let's try to run this command. It's okay, so now the command is working. I try to form connection again, it's working now. Now there's an interesting thing here. So now the interesting thing here is that we are still able to communicate here, even though the backlog size is 80, and we are blasting the server off right now. So, as I said, there are plenty of different countermeasures here. One of them was backlog. So reducing the backlog size would help us. So I've reduced the backlog size to, what was it, 80 or 128? But our attack was still not successful. The reason behind it is there's another countermeasure into play. That's called TCP matrix. So it's like a cache. You see how the most commonly used stuff gets stored in the cache, and if the CPU wants to access the same thing again, it will just grab it from the cache memory. And just like that, we also have some stuff over here that gets stored in cache. So these are the connections that get stored in the cache. So let's just open up let's just check how we can see where the things in cache. So but before that, let's just check the connections here. So net to confirm that things are working. Okay. So for that, there is this thing. So there's this whole command to check if there is any connection in the cache memory or not. So IP TCP matrix matrices. I don't know. Matrices. Shit. Matrices. Okay. What's it? Matrix. It's not a matrix. Matrix. Okay. Matrix. Short. IP TCP matrix. It's wrong spelling. Okay, I didn't know the spelling of this thing. Matrix, so yeah. So here you can see this whole thing was stored in cache. And interestingly, things that are stored in cache would be prioritized for anything. So even if our attack was successful, this thing was in cache, and the victim would just grab it from the cache itself. It doesn't even care if the buffer is filled up or not. Grab it from the cache and use it. So to remove this whole thing, we can just do TCP matrix flush. We'll be running this command to flush the cache. So now if you go over here, it's not here anymore. You see? So it's basically we have cleared up the cache. So the cache is now empty, and the thing that will come into play is only the backup. So now we'll double check. We can still access it. Yep, we can access it. And we'll try to do a DDoS attack then. So now the server, we are sending plenty of requests. We'll check the netscape test NAT, and here you can see all the SYN received. It's all the half open connections from different the randomized IPs, randomized ports are over there. It will be, it will just fill up super quickly. Okay, so these are all the netscape thing, and now we'll try to connect with this thing. Still able to do it. Reason why is it's still in there. Now we'll do TCP matrix flush. Flush it out. We cannot do it now. So basically our target, or you can say user number one, is no longer able to connect with the thing. We'll try to demonstrate it one more time. Stop the attack. And everything is now set. We'll try to. So right now we'll check the flash. Is there check the cache memory? Is there anything in the cache memory? There's nothing in there. We'll try to form a connection once. Oopsie. So right now I think there's still a couple of things in the backlog. Yeah. So there are all the requests already backlog is already filled up, so that's why we still cannot connect. What's interesting thing here that even though our tag we have stopped tagging, there are still requests in the backlog, and because of that we cannot access it. So it's still there. Okay. So we'll wait a bit and okay, we'll just start off all over again. So we'll start connecting with the things. Now we'll run TCSH, TC up, so that everything is up and running. TCS 26, we are into attacker. TCSH 76, we are into victim. And TCSH 01, we are into user number one. Okay, so now, as far as I think, there nothing has to be in the backlog anymore. Let's set less energy. Yep. So now backlog is completely empty, all peacefully. So we'll try to do one thing now. Try to 05 and 23. Now we can connect it with the victim, and if we check the what it's called IP TCP matrix. So it's not there right now, but let's close it now. Yeah, here you can see it's now in the cache memory. So like the previously, we can, even if we perform the DDoS attack, it won't work at all because the kernel, or if you precise it's called kernel, is the one who's dealing with this thing. Kernel will just grab it from the cache memory and use that half open connection from the memory instead of dealing with backlog and all. So for that, we will do flush, confirm that this thing is now empty, and we'll do Python ds. Oops, we'll go to volume first and clear this. So now it's blasting off with the different requests. Let's do this now. Yeah, so now it's all up and running, and we try to connect. It's not going to work anymore. So eventually, the poor victim is now out. Let's just try to do it one more time. Close this thing. and we'll try to see what exactly is going on with this victim now. So victim tries to connect here, okay, so it gets stored again now. Sure. Yep. So now that's how it's going to work. Okay. So here you can see if you try to connect it right now, and we are able to connect here because I restarted the machine and checked the backlog. The backlog is now back to 512. So remove the backlog to something smaller. Close this again. Okay, let's just make sure first of all, this project is flushed. That's all. And we will change the backlog to, let's just say 80. All right, so backlog is now 80, and we will close this again. Close this. Oops, flush. Okay, so the backlog is now 80, and we'll try to run this browser bar. And if you try to connect right now, it won't work for sure. Yeah, it will keep on trying for years and nothing will happen here. So eventually, that's how the task number one goes. And that's it for the task number one. But there's one more thing that you guys have to do. So you ran this Python script, and you also have to run. There is a C. Let's just show you guys. If you go to, of course, this one. So if you run this, you will only be having this file in your folder, synflat.c. So you also have to run this C file and check the output because there will be slight difference between your Python script and C script and C command, C program. So first of all, you have to install GCC compiler that I written down in this at the end of this lab menu thing. So you have to install a GCC compiler. So it will be if install GCC. Yeah, I already installed, but you have to install it now. So what I'll do is create an executable out of this C program. .c, and the output should be named Spain. Yeah, so now it's executable. It will do the same task to run the command. You can just go with censusing and put the IP address here 0.5. The port number is 23. We'll do the same thing. It will do the same thing. Going to blast the server off with the same request, but there is a slight delay, and you have to figure out what is the difference here. When you run the Python script and when you run a C executable, one of them may not work exactly well, and you have to write down what exactly is the reason why this one performed well and the other one failed in some cases. So yeah, that was only for task number one, I guess. Yeah, and also, yeah, so in 1.2, you're going to run this C program, and yeah, everything is explained it here. And there is also task 1.3. As I said, there is also syn cookie countermeasure that the connection will only get stored in memory once they're established. It won't store in half-open connections at all. So there is a lot of things going on behind the scenes, but yeah, you have to check that. So you have to turn on the syn cookie. There's also command for turning on syn cookie somewhere over here. Yeah, here you have to turn on syn cookie by running this command. Perform the DDoS attack and also have to make sure your Wireshark is running at the time and see what's going on, why the attack is not successful, what exactly is the reason behind it. And yeah, that was all for task number one. And number two, we are going to do the thing that I've said. We are going to kick one of the user out of the communication. So two parties will be communicating and one of them will be kicked out of there. So here there will be a couple of more things that we have to keep in mind, all the different flags and all that. So let's just go through it. I'm not going to go through the whole process of how we can perform this task because it's you have to do it yourself. I'll just show you the payload that you're going to use for your task. So you are given this template. You'll follow the same procedure, copy this thing, paste it on your machine, and then go to your volume folder and write it down here. So I have done the same thing and I think my yeah, here's my own payload that I got here. Not this one, oops. Just using this. Yeah, that's the one. So I have created a payload here. So let me just do the same thing and tell it. Try to connect with the victim. User one tries to connect with the victim on port 23. Use this username and password and everything is now set. I will also turn on the Wi-Fi capture and I'll be just sending some simple ls request or something, ls command or something. So now we get this capture file. At the end of capture file, as I've said, the attacker is going to predict what will be the next packet from user number one. So this is the IP of user number one ending with 6. So attacker is going to predict what will be the IP or what will be the packet for next packet for that user. So you're given a template here and you have to figure out these details like what will be the source IP, what will be the destination IP, what will be the source port and what will be the destination port, and also the flag will be set to R here. Like previously there was a flag set to S, and then you have to figure out the sequence number. That's like the most important part of this attack. So I have figured out everything for my side that was this my source IP was this, my destination IP was the victim. So here the source IP is basically the user one's IP and with six destination IP is this. Also just don't copy my details because it won't work at all. It will be different every time you connect with this victim using user number one. So it will be different every time. So let's just say sequence number will be different, the source port will be different. So here the destination port will be 23, flag set to R for the RST request. So RST request is basically the one we use to terminate the communication or connections. And then there will be sequence number. So sequence number will be which one trading what will be the next packet here. The sequence number will be shown up here. So if you go to the WhatsApp packet capture file, transmission control protocol, and over here, then we get the raw sequence number. So for sequence number, we are also checking one thing, that is the length of the previous packet. So the length was 0. So the sequence number of the next packet is like, let's just write it down here. It should be like sequence number plus length of the next packet. So this is what the next sequence number will be. So that's how you figure out your sequence number. So I will write it. For now, I will just do it in my own. It's 39450. It is not DDoS files. It's PQI. So I will just make sure the sequence number is different here. The sequence number is 2229. 295763. All right, so we got the sequence number, and we also, as I've said, the source port will be different every single time. So the source port over here is 39450. I will put 39450. So everything is set, and also you also have to write down the interface name in the payload. To get the interface name, you can just you can simply run ifconfig command on your host, like ifconfig. Oops, wrong spelling. Ifconfig. Oops, another one. Sorry. So we run ifconfig, and it's the interface, as I've said, it starts with br, so that you copy all this thing and put it in your payload, br and whatever. So let me just confirm it's ending with 52. Yeah, that's the one. So we'll save this file and we'll run this command now. So basically right now, as you can see, this guy is now connected with the victim. We are right now in the communication with the victims, so we will run our Python script. It's called um, SQQI for me. So I now ran my script, and interestingly, what I have capture file, you can see there is one red highlighted request packet. So this packet is RST, sequence number is ending with 23, same sequence number, and everything is same port. And now, if we check to this user one, that if it do something right, something down, you can clearly see here the connection closed by foreign host. So that means he's no longer connected with the victim here. So we have kicked this user one out of the connection. And in short, that's how we're going to do the RST attack, TCP reset attack. So we're not going to do anything special. It's the same thing. And at the end, it's also say you have an optional task that you can perform using sniff function, but it's up to you. You can use it as well. So yeah, it's just an explanation diagram that how you do this attack. Number three, we have session hijacking. Just like the name says, we are going to hijack the session. It's this button. And in the session hijacking attack, we'll be following the same procedure. We'll be looking at the communication that takes place between both the parties. So we'll get to the file now. So now I'll try to connect with the victim. So we'll write down my password. Also make sure to write every time you connect with this thing, just write down your log into the thing as well. Okay, so I've done every single thing. Now I have connected with the victim. User one is connected with the victim. And now as an attacker, I'm checking the network packets. There's nothing interesting going on here, but what we are interested in is predicting the next packet that user one will be sending out to victim. So we'll predict it. To predict the packet, we have to check a couple of things. So it's going to be an acknowledgement request. So we are given a Python payload here. In the payload, we are importing some couple of things that will it's the same thing. We'll be looking at the source, we'll be looking at the destination, what will be the source IP, what will be the destination IP, what will be the source port, what will be the destination port. However, here the flags are set to A. So as you can if you don't forget, if you can still remember, the flag was set to S in synthroid attack. The flag was set to R in the reset attack. But here the flag is set to A because we are sending out acknowledgement request in task number 3. And it will also ask for sequence number, follow the same procedure for sequence number and also the same procedure for the acknowledgement number. So here, if you check the last packet, we got the sequence number. We'll also check the length of this packet is 0. So the sequence number will be the same. Sequence number plus length. Sequence number is S1 plus length is 0. So it will be the same sequence number. And acknowledgement number will follow the same procedure. Length is 0, so the acknowledgement number will be the same as the previous one. And the source port is S1, destination port is S1. Also, one thing that you guys have to keep in mind is the source IP packet that you are looking at. So you're not going to check for the packet that is sent by the victim to the user 1. You have to check the last packet sent by user number 1 to the victim. That's the most important thing. User number 1 to the victim. And you'll check the content of this thing and create fill in the payload according to whatever you get here. So that's the thing we are going to do session hijack, and I will show you my own payload as well. Don't copy my own payload, by the way, otherwise it won't work for you for sure. So this is my own payload that I created for session hijack. Every single thing is filled up. So my source port was this guy was sending a request at port sending a request from port 55188, and the destination port was 23 because it was connected with telnet. Flag was set to a sequence number was the same as the previous one, and same goes for the acknowledgement number. Here, you have to do one more thing. It's not just that you are going to send simple requests, but you also have to send some interesting data here. And the data could be anything. Here we are going to place a malicious data here. Let's see, so still working here. So in task number 3, session hijacking. Yeah, here you can see I'm writing down that we are sending malicious payload. Malicious payload. Let me highlight this as well. Malicious payload. Oops, too much. Malicious payload. Yeah, we'll be sending out malicious payload here. The data part, you should put something malicious, like I've done it here. I just created. So what I've done, let me show you that. So in the victim side, in the victim's machine, if you press ls, it may be there or it may not be. I'm not sure if I created it for you guys or not. So I've created a file here. Well, let me just create new file touch. Let me see, or I'll just do it right away. So I'll do echo. This is a super important file. Do not touch this or you'll be fired. So I've created this file, and I will I've created the file name file.txt with the content of this. So if I create this file, this is not this the file.txt, it will show this thing. So let do ls, the file.txt will be here. Okay. So let's just say I've created a file in the victim machine, in the victim container, named the file.txt with the content of yeah, the content. This is the content. So this is pay in the payload. And the malicious is a malicious payload. What I've done here is I'll open up the here it's a secret.txt. I'll just make changes in this thing. So win or vs.py, not this one. Edge check here. So here what I'll do is I'll just create the file. So what this command will do is it will open up, read the content of the file.txt and pass the content of whatever the output is to this TCP stream. So here it's an interesting thing. So I have created, I will also have to create a listener here. So that I'll be using netcat. So netcat will be listening to port 9090. I'll do this in attacker instead. So netcat L 9090, and I will put an n% here as well. So n% would push the whole thing in background. It will be running in the background, listening to port 9090. And here the we'll try to open up this file and push the content of this file to this attacker's IP port 9090 where the netcat is listening to. So in short, once everything is done, we'll get the output of the content over here. So interestingly, what happens is we will be spoofing, yeah, here the user number we are sending request on behalf of user number one, or you can say is a spoof as a user number one to the victim. So the victim will be just in the request ask for the content of file.txt. So file will be opened up, and in the request you can see the content of file should be passed to this TCP stream that's listening to port TCP stream at port 9090 where the attacker is listening to. So I'll try to run this script, but before that we have to follow the same procedure that we have been following in last couple of tasks. That it will ask for source port, destination support, flag should be A and sequence number, and same goes for the acknowledgement number. Once everything is set, you will see something like this. Oops. Yes, I'll try to do the same thing now. Mm, So this 01 is basically user will get out of this thing. We'll try to connect with the user number victim again 10 dot 9 dot 4 dot 5. Port number 23, all good. Username, oops, can't do it again. Calculate this thing. Username is date, days, all set now. And we will try to capture the file. For that, we'll put a simple ls command to check what should be the last request. We got the last request here. We will check the length of this request is basically 0. So it will be the same as the output here. And okay, let's just go over here. Yeah. So let's just say I got this port source port is this. I'll write it down my source port over here. We'll get the destination port is 23. I'll write it down number 23 over here. It's already there. Flag is acknowledgement. Sequence number. The same procedure sequence number will be this one for me because that's the last request sent by this. I'll put the sequence number over there. Acknowledgement number should be this one because the length is 0. It's showing the same acknowledgement number. And this should be the malicious data for me. It won't be the same for you guys. You have to get any different payloads. But just make sure don't copy this thing because it won't work for you for sure. Okay, so once everything is done, we'll get an output over here. So we'll run, once it's done, we'll run our script. That is, I'll create, I've created a script that's Python 3 sq.py, whatever you can type in. So this Python script will run and drop the output. It will show up the content of the file over here. So I'm not going to run this because it will make things too clear. So, so this is how you are going to perform task number 3. The task number 4 is called creating reverse shell using TCP session hijacking. It's the same thing. You are going to follow the same procedure. There won't be anything different. So let's just let me just open up two files side by side. Good, and this is my garbage file that I've created. So, this, put this one. Okay. So the file name was various or something. Yeah. Here's the file that I have created for last task number 4. So there's not a not there's no difference between them. It's the same thing here. But instead of the preview, I'm just making change in these data section here. Instead of using this one simple command, you can use how to use this whole thing that's given in your lab menu. Yeah, you have to use this whole thing that's given in your lab menu, and you're good to go for that. So let me just explain this thing in a bit so you don't face any issues with this. So it's just going to run simple bin bash space I command, and the output of this command or whatever goes on with this command will be sent to this same thing, same procedure, same thing. And you have to see what exactly these two things are doing here. So 0 stands for standard input. In here, n% %a. So in simple words, you can say n% %a is anything that's coming from this stream. Anything from this stream is basically n% %a. Anything about this stream. So this one is doing is anything that's coming from this stream, this TCP stream, which is basically an attacker's IP plus port where the netcat is listening to. So anything that an attacker sends will get stored in standard input. And that standard input is of this reverse shell, this shell that we have created here. So basically, in simple words, is anything that any command that attacker sends will get executed in this shell. And just like that, number two is for standard errors. So here, the standard error, which is basically like an output. So standard output is different and standard error is different. Standard output is going to be one, standard error is for two. So here two is so here first of all we try to run a command in this shell. The attacker static command and it got executed in this shell. Now there will be an output of that command. So this is the output of that command that will get passed to n% one, which is basically the attacker. So what this two is doing is this one is anything the attacker sends, give it to the shell. And anything that shell pops out, like any output of the shell, send it back to attacker. So in sort of we got an interactive shell here, and it will be you can run as many commands as you want. So it's like a better version of task number three. We are going to follow the same procedure to get all the information like source port, destination port, and all that. And you will be just making the change in the data file here. So that was all about last task number four. And every single thing is well explained in the your lab manual. You can do it. And one thing that you have to keep in mind is, so once you think in the lab number three, if you have to fulfill lab number three, your Docker container of user 01 will stop working, will be jammed because you have messed up with the sequence number. So it will be jammed and you have to start up all the Docker containers again. Yeah, just keep in mind, and it will follow the same thing in lab task number four as well. So if anything starts jamming up, just go to this your tab where the Docker containers are running, press Control C. So it will stop all the containers. And once the containers stop, you have to start off all the containers again. Yeah, so now the container stop, you will start off all the containers again and will connect with this container one by one, like this thing. So that's all the thing you have to do here. And yes, you just have to submit your lab report and also with screenshot, everything needs to be well explained. And the most important part over here is you have to describe in every single task that you are performing, you have to describe what interesting thing that you are seeing here. So let's just go through all super quickly. What should be your task in this thing? Okay. So lab number one, you'll be performing a DOS attack, synflood attack using your Python script first. Then you'll do the same thing with your C program. You will also create an executable in your C program, and you'll be running that executable. You will compare the difference. There will be one of them will be working, one of them won't work, and you will explain the reason why. And you also have to, you can find that difference in your Wireshark Kepler file as well. So instead of whatever you find it, just write it down. And once it's done, there will be, you have to deal with the backlog file now because backlog will be an important part. You have to make change in your backlog size to make one of the program work. So also you can keep on checking the net to see the half-open connections in the list. If you write down WCDSL, then you can see how many of them are actually there. And as I've said, things get stored in cache, so you have to keep on flushing the cache. Otherwise, even though your attack is successful, you won't be able to make um the server down or make sure the server is down. So you have to keep on flushing the cache. So if anything shows up in the cache, you have to flush it as well. And then there is RS 1.2 using C language, which you have to show that C language your C program works and all that. When there is a scene cookie kind of you have to turn on the scene cookie and see if what's the difference here, why scene cookie is preventing this attack from happening. Then we are going to task number two. In task number two, we will do the same, not the same, it's going to be a bit different here. So we'll be listening to the communication that's been going between two parties, and check, we will try to predict what will be the next request from the um for user number one. We'll try to create the same packet of the similar packet that will be coming from user number one as in RST packet. So that RST packet and the victim will be like, hey, I think this one came from the user number one and he wants to terminate the communication or connection. So after seeing that RST packet, the guy will just terminate the communication with user number one. And eventually he'll be kicked out of the communication. They also say optional if you want to run an automation scan or something. Then there is a session hijacking attack. And session hijacking is we'll follow the same procedure, but here we are going to send acknowledgement request. So for acknowledgement request, the payload also requires you to have an acknowledgement sequence number or something. So the same procedure, you have to put the malicious data here. It's a necessary condition. You have to put the malicious data in here to confirm that your attack is successful. So it's the same thing. You can optionally use an automated scan here as well. What do you call automated script, so that you don't have to find out what's the segment number and all that. Then in task number four, we are going to upgrade a bit from task number three. We'll include reversal right away to get persistent access, and an interactive shell would give us access to run as many commands as we want as long as the server is running. So it will be all for this app. So yeah, good luck with this lab, and yeah, that was it.